this lecture I am going to introduce you to the concept of meshing. So what is meshing? The process of converting a geometric model like this into a FE model like this, which contains discrete nodes and elements, is known as meshing. The process is known as meshing. Coming to the element types used for meshing, there are 1D elements, 2D elements, 3D elements and other elements. So coming to 1D elements, where are we going to use such type of elements? So when we take a geometry where one direction or one dimension is very large in compared to other two dimensions, then we can assume or we can mesh that particular geometry with 1D elements. So see here, one of the dimension is very large in comparison to the other two dimensions. So the element shape is in the form of a line, and we need to be providing the other two dimensions in the form of a cross section to this particular element. And coming to the element types, let us say 1D element types, they are rod element, bar element, beam element, pipe element, axisymmetric shell element. So these are all examples of 1D elements. And in practical applications, when we have long shafts, beams, frame structures, pins and other sorts of structures, we may use these 1D elements to mesh them. Then coming to the next one is the 2D. So here when two dimensions are much larger when comparison to the third dimension. So for example, here in the plate, what happens, this length and width of this particular plate are very large in comparison with the thickness of this particular plate. So what we are going to do is we are going to use the 2D elements to mesh such type of geometries. So here the element shapes used is the quad elements and the triangular elements. And we need to provide the remaining dimension, which is nothing but the thickness dimension, to this element. And here the element types are thin shell, plate, membrane, plane stress, plane strain, axisymmetric solid, etc. are the type of 2D elements available. And in practical cases where we are going to analyze the sheet metal parts and plastic components with very minimum wall thickness, we are going to use the 2D elements in order to mesh such type of geometries. Then coming to the 3D, so if you have all dimensions with comparable values, then you can say it is a 3D object. And if it is possible, you can idealize this 3D as this 2D, or otherwise you can also idealize this 3D as 1D. For example, let us take the shaft. It may be a 3D, but you can simplify that particular shaft geometry into 1D to decrease the analysis time, analysis resources requirement and analysis. The element shapes available for 3D are tetrahedral, hexahedral, pyramid and other sorts of elements. Then there is no additional data you need to give for the element in order to perform the analysis. Then you come to the element type. It is a solid element type, and practical applications are where there is a solid body, you are going to use this particular 3D element, like say it may be a transmission, engine block, crankshafts, etc. And as I've told you, we can, wherever it is possible, we are going to idealize this 3D or simplify this 3D and make it as a 1D or 2D. And other sorts of elements exist like mass element, spring element, damper element, gap element, rigid element. So these are all different elements that are used to say simulate either mass, simulate the stiffness of a spring, or simulate the spot weld and other sorts of things. Then how do you select the type of element that you are going to use for meshing? So it is based upon three major factors. One is the geometry size and shape, then type of analysis, and time allotted for the project. So coming to the first one, type of geometry. So depending on the type of geometry, you are going to select the 1D elements. Here is an example of a body where this length is 1000 mm, but the dimensions width and height are 10 into 5. So what happens, this 10 and 5 are very less when compared to this length. So such type of geometries can be idealized with this 1D elements. So for example, see here, there is a long shaft. This particular shafts can be analyzed using this 1D elements. Likewise, if you have frames, steel frames or steel structures like this, you can idealize them in the form of a 1D beam, and you can analyze using 1D elements only. Then coming to the second one, here see the dimension, length dimension is 500 and the width dimension is 300, but the thickness is 2. So what happens when compared with the length and the width of this particular structure, the thickness is too low, and see here we are going to use the 2D elements in such type of geometry cases. These are the shapes of different 2D elements that we generally use, and these particular elements are available with every software, FEA software. Then coming to the application, see here we have an airframe where this particular total structure will be simplified as a surface, and analysis will be done by meshing this total geometry with 2D elements like shell elements. Then here is an example of a computer rack, sheet metal rack, which can be analyzed using 2D elements. Then coming to 3D elements, when all the dimensions of this particular body are comparable, then we will be using 3D elements. See, these are the different shapes of the 3D elements available. And here some of the examples of this 3D element modeling include like this transmission systems and this type of coupling systems and other sorts of systems. As I mentioned earlier also, if there is a possibility of simplification, we are going to use that simplification of 3D objects into either 2D or 1D, and then only we are going to perform analysis. So based on the geometry, you need to select what type of elements that you are going to use for meshing. And then the next one is the type of analysis. Say, based on the type of analysis you are doing, you need to select the type of element. For example, if you take the structural and fatigue analysis, if you come to 2D, the quad elements, if it is come to 3D, hexahedral elements are preferred over other type of elements because of the accuracy they give for the solution. If you come for the crash and nonlinear analysis, what happens? Priority to mesh flow lines and brick elements are given over the tetrahedron elements in order to get accurate results. Likewise, depending on the type of analysis, say for example, if you are performing mold flow analysis, then instead of all other elements, triangular elements are more preferred over the quadrilateral elements. So coming to the dynamic analysis, and depending on the type of geometry also, we have lots of types of elements that can be selected. Then coming to the final factor is the time allotted for the project. So for every project there will be some time. Based on the time, you can just use the automatic mesh generation tools, or otherwise you can also do manual meshing by setting up every mesh control, and you can check for this mesh. Automatic or batch meshing tools could be used instead of time consuming but structured, good quality providing methods. Then for 3D meshing, tetras are preferred over hexas. So what happens is, if you are going to put up hexas, the solution time will be more. So that is why if you want to reduce the time of the project, you need not have a lot of concern over accuracy, you can then go for the tetras. And there are other lot of factors which are included again into this particular time allotted for the project. So based upon all of these factors, you need to decide what type of element you are going to use, what type of settings you are going to use, how are you going to generate the mesh, are you going to generate the mesh manually, are you going to generate the mesh automatically, and there are other lot of factors you can select. So coming to the question, can we solve the same problem in different ways? Yes, we can solve the same problem in different ways. Here for example, we have taken a fixed beam where we have solved this particular beam in the 1D form as well as in the 2D form as well as in the 3D form. See here, coming to the 3D form, what happens? The number of equations to be solved was 52,344. Then coming to the 2D, what happens? The total equations to be solved are 54. So what happened? Around 10 times less. So the number of equations that are to be solved here are 10 times less when compared to the number of equations that are to be solved in this 3D case for the same problem. Remember, this is for the same problem. Likewise, coming to this 1D, so what happens? We have only 12 equations to solve. So this is much better. And remember, if we are going to follow everything, we are going to get the same result, approximately same result in the 3 cases. So what happens when there is a possibility? You need to take some assumptions and you need to simplify your geometry from 3D to 2D, and if it is possible, you need to change it from 2D to 1D as well. So we can solve a same problem in different ways. Then finally, what are different meshing steps? So first thing is, you need to sufficiently understand the geometry. So what are the features that are present in the geometry? How can I mesh this particular geometries? How can I say use the different settings to accurately convert each feature? For example, let us say if you have a straight face, it is easier to mesh when compared with the circular face. So you need to study the geometry, and once you study the geometry, you need to estimate the time. So you need to estimate the time of generation of the mesh as well as time to solve the particular problem, and what is the accuracy required also you need to keep in mind. So depending on the accuracy required, you need to perform the time estimation. Then coming to the third step, we are going to have to check the geometry. So once we are going to import the geometry from other CAD systems, we need to check whether during the transfer process are there any losses that are created, or is there any data loss that has occurred. Then fourth one is symmetric check. As I have told you, we need to say decrease the size of the model in order to increase the efficiency of the problem. Then for that purpose you can do symmetric check, and if there is symmetry in the object, you can decrease the size of this particular model. And then you need to select the type of elements that you are going to mesh the object with, and you also have to set the mesh settings. So what happens is there are number of mesh settings like selection of edge length, selection of different types of elements, different types of methods to say mesh the geometry, and other lot of settings are there. You need to master all those settings, and you need to select all those settings. And once you selected all those things, then final thing is you need to select the contact meshes, and you need to model the joints. And once you have done all these things, you can generate the mesh. So these are some of the steps that are followed in the industry while performing a mesh. And once you are satisfied with all these steps, you can just go and just generate the mesh and send it to the FEA engineer. In the next lecture, we are going to see some of the global mesh controls that are present, which are very useful in generating mesh inside ANSYS Workbench. To demonstrate the global mesh settings inside ANSYS Workbench, I have opened ANSYS Workbench. Right now, I am going to just go to the component systems and drag and drop this mesh component system onto the project schematic, because here we are not going to apply the boundary conditions and we are not going to solve the problem. So I am going to take just mesh system here, and once I take the mesh system, I need to right click on the geometry cell and go to import geometry, and I need to browse. And once I browse, I need to go to this location where I have this particular file. So here I found the geometry that I need to mesh. Then I have opened it, and once I open, I can just double click on this mesh cell, so that ANSYS Mechanical will open with the mesher on. ANSYS Mechanical will open, and once ANSYS Mechanical opens with the geometry, then we are going to apply some global mesh controls, and we are going to see what are those global mesh controls. So coming here, see, here is a body with some straight faces, straight edges, as well as circular edges with holes and other sorts of things. So as I told you, we have automatic mesher that is inbuilt into ANSYS Mechanical, which is very efficient in generating meshes, initial meshes. For example, if the body is very simple, the automatic mesher is going to very accurately generate the mesh. But if the complexity of this particular geometry is going to increase, this particular mesher can be used to create an initial mesh, and from that initial mesh we are going to use some localized controls to generate more efficient mesh. For now, what are we going to do is we are going to go to this mesh group. Once we go to the mesh group, see here, the first and foremost option is known as the physics preference option. So based upon the type of analysis you are going to perform, this particular automatic mesher inside ANSYS Mechanical will change the settings. For example, I have set the physics preference to mechanical. What I am going to do is I am going to just right click, say generate mesh. So once I generate the mesh, now what I am going to do is I am going to go to the statistics, and see here in the statistics the number of nodes that are generated are 7130, right? So now what I am going to do is I am going to go to the physics settings, and instead of mechanical I am going to select CFD. So what happens in CFD, we need more finer meshes. So what happens, the automatic mesher will be increasing the mesh density. So I am going to right click, say generate. So now once I have generated the mesh with this CFD physics preference, see what happens. The number of nodes has increased to 40,669. So what happens, we definitely have an effect of this global setting, which is nothing but physics preference. Likewise, you can also select the type of solver. Generally, you have 2 to 3 different types of solvers inside ANSYS Workbench for performing CFD. So what happens, you have Fluent solver, you have CFX solver, you have Polyflow solver. So you can also select the settings from here as well. So I'm going to just go back to mechanical and I'm going to just remesh this particular object by just right clicking and say generate mesh. So the next option we are going to see is the relevance option. So relevance is nothing but you will be having a setting where you can control it from -100 to +100. So what happens if you set the relevance to -100, say, which is the minimum value, then what happens when you try to generate the mesh with some settings, it is the coarsest mesh that you are going to get with those specific settings. So I have selected the physics preference to mechanical. So I am going to just keep the relevance to 0. Then I am going to generate the mesh once again. See, I am going to generate the mesh once again. And once I generate the mesh, you can see the number of nodes are 7130. Okay, then what I am going to do is I am going to set up the relevance setting to -100. So what happens, this particular number of nodes and elements should be decreasing, because what happens, -100 is the minimum relevance value. So I am going to just type in -100 and I am going to press OK. Then I am going to just generate. So once I generate the mesh, you can clearly see from this picture as well, the mesh density has decreased. See here, the number of nodes have changed from 7130 to 2349. So what can I do? If I just set the relevance setting to +100, so if I take it to +100, see, if I take it to +100, what should happen? It should increase the mesh density. So I'm going to just right click on this and say generate mesh. So instead of 7130, I should be getting more number of nodes. So see here, the mesh density has clearly increased and the nodes, number of nodes have increased to 21,515. So what happens with the relevance setting? So in the automated mesher, you have some default settings. Based upon that default settings, if you are going to put up the value of relevance to -100, this is the coarsest mesh you are going to generate with these settings. But if you are putting it to +100 with the specific settings, you are going to generate the finest mesh. This is one setting. Then coming to next one, you can go to the sizing group. In the sizing group, you have what is known as a relevance center. In the relevance center, you again have three settings. One is the coarse, other one is the medium, and other one is the fine. If you want to generate the coarse mesh, you are going to put up coarse. And in the coarse also, if you put relevance 100, this is the minimum coarse mesh that you can generate with these settings. So for example, if I change it to fine rather than coarse, so what happens, see here, the number of nodes must be increasing because the mesh density is going to increase, because previously we have generated the mesh with coarse settings. Now what I am going to do is I am going to just right click, say generate. So once I say generate, see the number of nodes will be increasing from 21,000, and I think the relevance is 100, so it will be increasing multiple times. If we are going to change it from coarse to fine, what happens? See, the mesh density has increased tremendously, and see, instead of say 21,000, the number of nodes were around 2,38,000. So this is how you can change different settings. If you want a coarse mesh, you can just go back and say coarse and you can regenerate the mesh. Then coming to the next option is nothing but the element size. So element size means you can give a default element size, and based upon that element size, the automatic mesher is going to generate a mesh. For example, if you have a 10-meter bar and you give the element edge length as 0.5 meter, then what happens? The mesher is going to generate a mesh of 20 elements, each of 0.5 meters. Likewise, if you give the element size, it is going to generate. For example, we are going to see here, I am going to go back to the coarse mesh and I am going to just generate the mesh. And once I regenerate the mesh, right now what I am going to do is, okay, I will also reduce this relevance to 0 so that I can get a coarse mesh for this purpose, for demonstrating purpose. Then coming to the next option, we have what is known as the size function, and based upon this size function, we get more control over the global mesh settings. For example, let us say if we have selected this curvature setting, what happens is at the curvatures, if the body is having lot of curvatures, at this particular curvatures, you will be getting more finer mesh, or you will be getting more structured mesh. And if you select the proximity, see for example here I am going to select the proximity, and see here, I'm going to show you. So at this particular edge, this particular circle and the edge are very much nearer to each other. So what happens in the default settings, I don't have any refined mesh here, but if I select the proximity and generate the mesh, see here, without increasing the mesh density here, it has increased the mesh density here where there is two features in proximity. Likewise, if you have curvature, if you put the curvature setting, you are going to get more finer mesh on the curves. This particular proximity feature will be helpful when there are lot of features very nearer to each other, and if you have lot of curvatures on a body, you can use the curvature option, or otherwise you can add proximity and curvature so that both of the settings can be applied to this particular body at the same time. And coming to the next option, which is nothing but the uniform option. So what happens is you are going to give the element sizes, and based upon the maximum and minimum element size, it is going to generate the mesh. These are some of the global mesh settings you need to be knowing in order to create efficient mesh for your simulations. In the next lecture, we are going to see some of the local mesh controls which are pretty useful for us to generate efficient mesh inside ANSYS Workbench. Now coming to the local mesh settings. So what I am going to do is, in order to create a local mesh setting, you need to just right click on this mesh group or mesh branch and say insert. In this we are going to see method. So the first option is method. So in the method, first you need to select the geometry. So I am going to select the total body and say apply here, and here by default the method of meshing is set to automatic. We have two types of we have different methods like tetrahedrons, hex dominant, sweep and multi-zone. A mesh dominated by tetrahedron elements will be created. Likewise, hex dominant means a mesh dominated by hexahedral elements is going to be created. Likewise, multi-zone means it creates a free mesh where it is a combination of tetrahedrons, hexahedrons and other type of elements. So you can directly leave this particular option to the automatic mesher, or otherwise you can just add a manual setting so that you can select what type of mesh you are going to require. And then the next local control is you can just right click, say insert, and go to the sizing. So instead of changing the size to the overall body, if I want to change the size at a certain feature, I can use this local controls. If I want to change the element size here only on this particular line, I am going to select this line and I am going to say apply, and I can give this an option. So here by default the element edge length is 0.84 inches, but I want to change it to some 0.2 inches. So I can just type in the element size. Now what I am going to do is I am going to generate the mesh to show you the effect. So once I generated the mesh, see here the mesh density is remaining same here, but what happens when this particular mesh is coming to this line, it has been refined because of the element edge length, that element size that I have provided to this line through localized mesh control. Then the next one is we can right click, say insert, and we can go to this refinement as well. So if you want to refine mesh on any feature, or if you want to refine mesh on any part throughout an assembly, you can use this refinement. Here we have three refinement levels: the refinement level 1, refinement level 2, refinement level 3. So based upon these three refinement levels, the refinement of the mesh is going to occur. See, for example, I am going to just show you. See, I am going to just show you the mesh here. So at this particular line, you can observe there is a coarse mesh, but I want to refine this particular mesh. So what I am going to do is I am going to go to this refinement and select this particular edge. Instead of face, I am going to select only this edge, and once I select this edge, I am going to press apply, and I am going to give the highest level of refinement, which is 3. So 3 means maximum number of elements will be created with these settings. 1 means minimum number of elements will be created with these settings. So I'm going to just enter 3 and press enter, and I'm going to generate the mesh. And you can see carefully, if you observe carefully, you will be able to see that a lot of refinement has occurred at this line only, and other areas the refinement is not done. So likewise, you can also decrease the refinement. I have decreased the refinement to 1, and I am going to just update the mesh. I am going to update the mesh. See here, when I have a refinement setting of 3, I had a more finer mesh, but here I am having a refinement level of 1, I have a coarse mesh. With whatever the options that you have learnt let us say the global settings as well as the local settings, you will be able to efficiently create meshes for a number of problems. But if you want to create meshes for very high-end geometries, then you are going to need to learn how to generate efficient meshes and other advanced options which are a course onto themselves. In the next lecture, I am going to tell you about what are the different mesh metric systems that are used to quantify the quality of the mesh generated on the geometric body, and we are also going to see where we can access those options inside ANSYS Workbench. I am going to talk about mesh quality metrics. So what are the different metrics that can be used to quantify the quality of the mesh that you have generated for performing an FE analysis? Here we are not going to talk about any theory, we are just going to know what are the parameters and what are the values of these parameters which correspond to a good mesh. So the first one is the aspect ratio. So here the aspect ratio will range anywhere from 1 to 20 and to infinity, and if you want to have a good mesh, you need to have an aspect ratio very much nearer to 1, and if it is anywhere from 1 to 3 it is somewhat okay, but if it is crosses 3 it is not okay. Then coming to the next one, it is known as the Jacobian ratio, and this Jacobian ratio also varies from 1, which is perfect, to infinity, which is bad. So this particular value can range anywhere from 1 to 5 to be said as a good mesh, but once it crosses the 5 value, the mesh quality is going to get deteriorated. Then coming to the third parameter, it is the warping ratio. So for 2D elements it is going to range from 0 to infinity. Likewise for 3D elements also it is going to range from 0 to infinity. Coming to 2D elements, if you want perfect mesh, this warping ratio should be near equal to 0. If it is ranging from anywhere from 0.01, then the mesh is good, but if it is crossing 0.1, the quality of the mesh is going to deteriorate for 2D elements. Then coming to 3D elements, if the value ranges anywhere from 0 to 0.2, you will get a good mesh, and once it crosses 0.2 to 0.4 it is okay, and if it is going to cross 0.4 the mesh is not good. Then the next parameter is known as parallel deviation, and this parallel deviation also ranges from 0 to say 170, and if you are going to get a value anywhere nearer to 0, then you can say you have built a good quality mesh. The next parameter is the maximum corner deviation. In this, if we are going to have a 3-sided element, it is going to range anywhere from 60 to 165. Likewise, if we are going to have a 4-sided element, we are going to have anywhere from 90 to 180. In order to get meshing good, you need to aim for this value which is very much nearer to 60 for a 3-sided element, and then coming to the 4-sided element, the value of maximum corner deviation should be anywhere nearer to the 90 mark in order to achieve good mesh. The next parameter is known as the skewness. So it ranges anywhere from 0 to 1. If you have any value ranging from 0 to 0.6 or 0.5, you are going to have a good mesh. Then if it is crosses 0.5 to 0.7, it is okay, but if it is going to cross 0.7, you are going to get a low quality mesh. The next parameter is known as orthogonal quality. So if you want to have a good mesh, then this particular value of the quantity should be anywhere nearer to the 1 mark rather than nearer to be 0. If you are having an orthogonal quality nearer to 0, then you are going to have a low quality mesh. And these are the different quality metrics that are used to study the quality of the mesh that is generated onto this particular geometry. Then remember, all of these things are based upon the type of geometry you are meshing and type of accuracy you require, and it all depends on a lot of other factors. Now we are going to open ANSYS Mechanical, and then we are going to see how we can access all these quality metrics inside meshing module of ANSYS Workbench. So see here, I have opened ANSYS Mechanical, in which we have done the meshing. So once you have done the meshing, you can come to this details view, and in the details view you can select the quality. You can expand the quality group. In this quality group, you are going to get all the metrics that are required for testing the quality of the mesh that is generated on the geometry. So for that purpose, what I am going to do is, here there is an option called mesh metric. In this, I am going to select whatever the type of mesh characteristic or mesh quality test I want to perform. Then coming to aspect ratio, I am going to select aspect ratio. Once you have selected the mesh metric, here in the graph area a bar graph will be visible, and from the bar graph you can see this is the type of elements that were used to mesh this particular geometry. See here, that means tetrahedron elements were used to mesh this particular 3D objects. And you see here on the x-axis you are going to have the mesh metric. Here the mesh metric is aspect ratio, and on the y-axis you are going to have the number of elements that were created while meshing this particular geometry. Then here my lowest quality of aspect ratio is nearer to 1.20, but from the mesh quality chart we can say that this particular value of aspect ratio should be very much nearer to 1 in order to get a good quality mesh. So see here, it is somewhere around 1.7 or so. We can refine this particular mesh and we can just improve this particular quality. So what I am going to do is, I am going to go to this mesh group and I am going to increase the relevance without changing any other settings. So I have increased the relevance to the maximum point, and I am going to right click, say generate mesh. So now once I have refined this particular mesh, see here the particular elemental quality has improved and it has come down from 1.20 to 1.17. And likewise you can select any of this particular mesh metric and find out how the quality of your mesh that was generated. Then coming to the graph here, if I am going to click on any of this particular bar, you can see it is highlighting all the elements that are having this particular characteristic. So if I click on here, it is going to highlight what are the elements that are having an aspect ratio of above 4. Likewise, I can also click on here and I am going to see that there are 2 elements which have the quality of aspect ratio of around 22.77. So this is how you can use the quality metrics present inside ANSYS Workbench to perform quality analysis on your generated mesh. In the next section, you are going to see how to perform structural analysis inside ANSYS Workbench. Thank you.